Hello, I'm Ian Kageber.
And I'm MaryKate.
And we are McKeon Incorporated with our Mean2 processor.
So we choose Mean2 as the name of our processor. Mean is an English word meaning error-bearing, especially expressive of attitude or personality. Coincidentally, it also means premiums in German and time in Maltese, which both money and time are important aspects of our processor.
So the basics of our processor, we have done a dual-core implementation of this processor. We use Harvard memory architecture in little endian format, as well as a shared bus that shares data among multiple cores, and we manipulate both integer and floating point data.
So basics of our instruction set is it is a modified reduced instruction set computing RISC type core. We have 85 available instructions, so 5 more than baseline, which are used for multi-core operations. All instructions are 32 bits in length, with the exception of 4, which are 64 bits, with 32-bit trailing immediates. All our instructions use a consistent format, and all are multi-cycle instructions, varying between 3 and 6 cycles. So here's our basic instruction format. This instruction format is also can be modified for the 32-bit immediate, which will just add a word on the second line, or 24-bit immediate, in which all source registers and zeros contain a 24-bit value. 8-bit immediate, in which source 2 register is taken out and replaced with an 8-bit value. 2-bit immediate is for our enhanced instructions for multi-core operations. It's a core select, and that would be in the least significant places. We also have a register indirect format.
So here's our top-level overview of our processor. As you can see, we have 2 cores implemented in this processor. We have core managers down here. As you can see, we actually have 4 of those. With the setup of this processor, it has the ability to implement 4 different cores, as well as memory controllers and memory mapped IOs.
So each core consists of a control unit and execution unit. The execution unit being made up of an integer data path and a floating point data path, as well as bus interface unit, which provides both an interface between the data paths and the other in memory, as well as holding our special purpose registers.
So the control unit is one of the biggest parts of this project. It is the state machine which controls the execution of our processor. It also outputs the control words to both the bus interface unit and the floating point data paths. Some of the instructions require more than 1 clock cycle to execute, and that is implemented inside the control unit.
Our execution unit consists of 3 main modules. Each data path module performs operations on its specified data type, and the bus interface unit provides the interface between the core and the device manager. The bus interface unit has 5 outputs. The flags register intended for control, and a instruction register line used by the control unit, as well as 2 10-bit address lines and a 32-bit bidirectional data line, which go to our device manager.
The bus interface unit is the interface between the core and the devices, including the instruction memory and the data memory and the I/O mapped memory. It has several registers, including read and write buffers and more, which will be discussed in just a moment. It also contains a multitude of multiplexers, which control the data output and the address output of the core.
It also contains our special purpose registers, which include the instruction pointer, which contains the address of the next instruction to be fetched, our stack pointer, which is increment before decrement after structure. The instruction register, which includes the contents of the instruction currently being executed, and the memory address register, which has the memory address that is going to be accessed if that is used. It also contains our flag register. So we made our flag register a 32-bit register, which allows for possible expansion. The 6 most significant bits include the floating point flags, which are set whenever any floating point operation occurs that uses 2 input operands. Our least significant bit is our interrupt enable flag, which is set in software, the interrupt enable instructions. Each core can have the interrupt set or cleared, separate from each other. And then we have 4 flags for integer data path, which are set with logical and arithmetic operations.
Our core, our processors have multiple I/O capabilities. We have I/O mapped memory, which is very common in embedded systems, including write-back memory for non-mapped devices. And the lower addresses are reserved for controlling the multiple cores in this processor.
So here's our device manager. So our device manager includes 4 core managers, each available for the 2 cores, and then plus 2 extras for expansion. And then it also contains 3 memory controllers, 1 each for the I/O, data, and instruction memory. And then finally we have the memories themselves, which are there, yeah. So it's contained in system-on-a-chip style.
The core managers themselves is what controls the execution and the availability of each core. Core 0 is the highest priority and is enabled upon reset. The other cores are disabled upon reset. We included a new state at the very beginning of execution, which fetches from these core managers the reset address of the core. And these core managers control whether or not each core is clocked or disabled.
The memory controller, which 3 are instantiated, control what the access to the data lines inputs to the memory. They all prioritize the higher level core's memory requests, so that core 0 always has the highest priority. And they also block execution of lower level cores if higher level cores are also requesting memory access. And then the memory controller also selects the correct address and read-write select dependent on the access given.
We have added 5 new instructions for multi-core operation, which is core wait, start core, stop core, sending of registers, and accepting of the previously sent register.
So the core wait instruction blocks core execution and another core calls the wait instruction, which allows for core synchronization. So how this works is that the one core executes the wait instruction, the first core to do so waits until another core also executes that instruction, and then both continue.
Then we have start core, which in our implementation of this ISA can only be called by the core 0. Other implementations may allow other cores to do it, but core 0 is the manager core in our implementation of this ISA. It sets the instruction pointer to source 1 register, and it sets the core as active as specified by the 2-bit immediate value.
And the stop core instruction works similarly to the start core instruction, except it sets the active to false and stops the execution of secondary core. It also sets the IP of the secondary core to a selected value.
The send register stores an IDP register, the integer register, into a temporary register for transmission to a secondary core. It sets the data as ready to be read by the next instruction that we implemented.
Can you elaborate the purpose of that?
This is to allow communication of data through, from one core to the other. So if you're trying to send a specific memory location, you can send that as a register over to a secondary core. That's how we implemented it. With the 14th test module, we implemented it twice inside of our core. We began the second one at a different memory location and sent it its data memory location to write to.
And then that works in conjunction with the accept register instruction, which reads the value of the pass register and stores the value in an integer register, and sets the pass register data as dirty. So our pass register can be read only once for every write, but it can be written to multiple times. Also, the core that writes the pass register can also read it, so you can use it as an additional register. If the data is dirty, the core waits until the other core sets the writes to the data, and then it will read it and continue as well. And then once it's read, it's no longer ready to be read.
This prevents the core from reading invalid data or data that has not been written yet. Further points to consider would be core 0 is always the highest priority. So the system should be, in an RTOS-based system, should be implemented on core 0. All the other tasks can be implemented on the secondary cores. Semaphore should be implemented at an OS level. Pass register is great, but if you're trying to send structures or high-level programming data, you would want to implement it as a semaphore. All enhanced instructions can also be implemented with in and out instructions because they implement the memory mapped IOs. And always remember to set the stack pointer of each core to a different location, otherwise they will override each other's stacks. It's a good thing to consider.
Feature enhancements that would be useful for this processor is that it may be valuable for a more sophisticated mode of prioritization to be put into place. Right now, the lowest level core always has priority. The lower core number always has a priority. So if more cores are added, then we would want to perhaps change that. Another thing is if we do add more than 3 cores especially, it's necessary absolutely to add cache memory because of it's a multi-cycle approach to architecture. Without that, the last core would pretty much never execute because the fetch state always reads memory. It would just have to wait. Also, the core wait and pass register instructions should be enhanced to target specific cores if more than 2 cores are instantiated. Right now, they don't discern which core is accessing memory, which works fine for 2 cores, but more than the data could become corrupted if different cores are communicating. Also, the pass register instruction could be altered to trigger an interrupt, signifying the data is ready, rather than having it be a polling approach.
Thank you. Do you guys have any questions about our core? Yes.
All right, so you guys talked about interrupts. I was wondering because you have multiple cores, how they handle a single interrupt.
They can both implement interrupts. So they both actually get the same interrupt signal, and they can implement interrupts in a completely different way.
So do they have separate interrupt enables?
Yeah, they're set separately. So one core could be enabled and the other could not.
They run the same ISR. You can set a register inside the core to let it know which core it is, which ISR to run. But this allows both of them to get the data from the interrupt, if need be. Yes?
Okay, so you talked about prioritizing the cores, running the instructions. Now, from what I gather, they don't just take turns running instructions, right? They don't switch off. Now, there has to be some kind of algorithm that the compiler produces to which, why one core is executing instruction depending on what it is. Like, when does the other core start executing the next instruction, or is it a simple approach, or is it something more complicated than?
No.
It's a fairly simple approach. If both core 0 and core 1 are requesting, say, data memory, core 0 will get the data memory first. Core 1 will have to wait until core 0 has finished accessing data memory. That's the approach we took. That's why we say with caching, we can implement this at a much faster rate because the data can be cached and ready to go right then and there.
So you have two cores trying to feed off the same data memory, so cache definitely would need to.
Yes, that would
Help it out,
significantly increase it. Yes.
What happens if, like, there's a jump or a call instruction? How do both your cores handle that in terms of IP?
They have different IPs. They are
Okay.
complete.
They're not running the same program.
Yeah.
It's
Okay.
the CPU itself is duplicated twice.
Okay.
One of the main features of the way we implemented this, we can take in almost any core with a slight modification to it and run it as a dual core in our system.
Okay.
Any core running the baseline ISA as specified by this project. Any other questions?
Core managers. So they're just boxes to us. What is it? What's inside of a core manager? What is it? What does it manage? What's it do?
It's a lot of
You didn't have any examples or like how's it implemented?
it's a lot of just logic. It takes in all the it's just a simple register actually. These are a lot of logic. This is simple registers with one bit register saying whether or not the CPU is active and another 10-bit register specifying the reset address of each core.
Like you don't have a slide that shows us what that is? Like a core manager, boom, this is what it is.
We talked about it earlier on in the presentation.
Yeah, I know.
Yeah.
I just illustration to help visualize what's going on.
We do not have a
Oh,
slide
okay,
for that.
okay. How about the memory controllers? Any, just to help us? We don't know what you did. How's it implemented? What's the design of a memory controller?
It's a lot of logic. It's just a lot of AND gates inside of that.
We just ran out of time.
It's a lot of ANDs and muxes inside of there. Just
But what's it doing?
it's choosing. It takes 4 inputs right now because we only have 2 cores. The inputs it takes in are the data address lines, or the address lines for that memory, as well as the chip select, the read select, and the
Okay.
write select. And depending on which core is requesting data, it selects the correct address and read and write select, and sends it over to this guy and puts it out onto the data line.
So is there a core select also that goes in there or something? That
It's
prioritizes which address to use?
It's implemented using the chip select. So if they're requesting the chip select on the data memory,
Got it.
that's how you.
Got it.
Yes.
So when you guys ran your enhanced instruction set, did you have to put in your? You mentioned 6 new multi-core control words. You found yourself putting those in between each instruction to kind of tell which core was doing it, or was it managed automatically from your hardware?
Please elaborate on your question.
So you mentioned those 4 control words, right? When someone writes a program for your processor, they have to implement those
Yes.
ones?
That's
Okay.
correct.
Yes.
The programmer.
This will, without any modification to the original code, this will run on a single core, as would it would run the baseline.
So our baseline just runs on core 0, basically, where we make a new program in order to run both cores. It explicitly calls the other core.
Both core have their instructions in instruction memory. Core 0 tells core 1 where in the memory to begin executing when it's enabled.
Thank you. That really elaborates.
So no examples of like modules that you ran to show that it worked or how it worked?
They're in the ISA.
I know, it'd be just for the audience or for our edification.
Yeah. We
Just
didn't-
ran out of time, you said.
Well, we ran out of time
Well-
for diagrams. We just didn't think it would be that interesting to show code. Originally, we had code on there, and
Mhm.
we just didn't know how useful it was for the audience.
The implementation, the memory module 15 as we called it,
Mm-hmm.
is a duplication of memory module 14 running twice, with each core writing to different memory locations. Core 1 starts core 2, core 0 starts core 1, tells it where to write its data to, and waits for core 2 to begin and synchronize using the core wait. Once they do that, they begin execution. Then near the end, core 0 turns off core 2, and you can actually see that it finishes its last write cycle, and it is hung and paused there until core 0 tells it to begin again, but core 0 halts, and that's the end of execution. Yes?
Is there? You mentioned your name, mine too. Like, is it pronounced mean or mine?
Mean.
Oh, mean too.
Mine
okay.
is spelled
E-I-E-I,
Yes.
right?
Were you asking if there was a version 1 or something?
Yeah, well, like, it's mine
there was
too.
a-
Like,
there was a
The-
version 1.
The
It was
version
like
1 was the baseline
baseline.
implementation. This is the 2 because it's a dual core with enhancements for support up to 4 cores. Why we say 3 cores is the theoretical maximum, if each core is running in its most efficient state, which is fetch, decode, execute, fetch, decode, execute, the memory is always, instruction memory is always being read. Data memory is always being read. And they are always executing. So core 4, without caching, will never be able to access the data because it's the lowest priority. Yes?
So are the separate cores fetching at the same time or separately at different clocks?
They are fetching 1 clock offset.
Okay.
They are asynchronous to each other. That's part of what the core wait is for, to synchronize the cores and begin execution again.
so is it synchronous to core 0, and all the other cores
They're-
you don't match up to it?
They're just which cycle they are of the fetch, decode, execute phase is off. They're doing it at the
With-
same time. So they're
But they're synchronous to the same clock, though,
Yes.
right? Okay.
With pipelining and caching, the cores can be synchronized, but without that,
Yeah.
they both have to wait for data memory and instruction memory and IO memory. Are there any other questions?
Awesome.
Very
It's very, very good. Thank you.